Hello everyone, I'm Sneha Padgalwar. I'm the software engineer at Meta, based out of London. I joined Meta 2 years back, and since then I've been working in the privacy infra org. My main focus area has been deletions. So today I'll be presenting my favorite topic, which is scheduled deletion. So before moving forward, let's go through a few deletion use cases. Many of you might have used our apps to upload pictures. I generally do it to upload pictures of my dog. Has it ever happened to you that you uploaded a picture and you're not satisfied with it? Happens a lot with me. That's when you go and delete it. This triggers the deletion flow for the removal of the post. Another deletion use case is user account deletions. This is when the user wants to delete his entire account. Now we have a good understanding of a few deletion examples. Let's move on to the agenda of the presentation. First, we'll talk about the scheduled deletion infrastructure. Then we'll understand deletion framework. And next, we'll in the end touch base on future work. Scheduled deletion infrastructure. The examples we spoke about in the previous slides were all user initiated deletions. That is, when the user clicks on the delete button, the deletion is triggered. But a large part of our data at Meta is ephemeral in nature. That is, for example, Instagram and Facebook stories, which need to be deleted after they reach a specific time, which is called the TTL, time to live for the object. The scheduled deletion infrastructure was built to handle these ephemeral objects. Now let's talk about the different types of ephemeral objects we have. The first one is the dense objects, whose TTL are defined at the create time. The example for it is Instagram stories. The next is the sparse type of objects, where the TTL is defined after the creation of the object. Example for this is the recently deleted feature available on Instagram. Here, when you delete the post or the media, it basically goes and sits inside this folder and is deleted after 30 days. Now, let's move on to the high level overview. The scheduled deletion infrastructure and the deletion framework sit on top of the schematization layer at Meta. We do so because we want to provide easy to use APIs for developers and make sure that it is difficult for them to do the wrong thing. The objects, which are ephemeral in nature, that is, have a TTL associated with it, go through the scheduled deletion infrastructure. And the objects which don't have TTL directly go to deletion framework. Now, let's talk about the challenges we faced while building scheduled deletion. The first one is, how do we determine the TTL for the object? For this, we build the decision engine. Now let's understand, how do we identify the objects have reached their TTL. For this, we have created the aggregation pipeline. Next, and the last one is, how do we delete these objects? For this, we'll be using the deletion framework infrastructure already available at Meta. Now, let's go through each one of these in detail. The first one is the decision engine. All of the ephemeral objects which are onboarded onto SD are associated with decision engine, which tells us the TTL for the object. That is the time when this object needs to be deleted. Now, the output of the decision engine can be one of these three actions. The first one is delete immediately. As the name suggests, this means that you want the object to be deleted immediately. The second is cancel, which means that we no longer want to delete this object. The last one is reschedule, which means we want to schedule the object for deletion further in the future. Now let's go through an example decision engine. As you can see, this is create time decision engine. Here, the TTL value depends upon the create time of the object. So the ephemeral objects which use This decision engine will be scheduled for deletion at a TTL time, which is the sum of the create time of the object and some static value. This is one type of decision engine. We also provide custom decision engines where developers can write custom logic based on their products, which will decide the TTL at runtime. For example, if you want to delete a post 10 days after the last comment. Now, let's understand where decision engine fits in the scheduled deletion infrastructure. Now, on a high level, when the object creation takes place, we run the decision engine, determine the TTL, and log it into the daily job table. Once we have logged all the ephemeral objects in the log table, the next step is to scan all the logs and identify which objects need to be deleted on a given date. Now, this sounds pretty straightforward, but it gets complicated when you're dealing with trillions of objects. Hence, we created the aggregate pipeline for the scanning purpose. Now, let's understand how aggregate pipeline works. This pipeline is responsible for effectively moving data from daily job table to the aggregate table. Before we move forward, I want to highlight a few things. The tables we are using here are the data warehouse tables which are used internally at Meta. When we were developing this infra, after considering a few storages, data warehouse came out to be the most cost effective. As we know that we were dealing with trillions of objects, hence trillions of entries in the log table, the version of data warehouse we were using didn't allow row addition or deletion. By this, I mean that addition of a row required rewriting the entire table or partition. Hence, we can say these tables are immutable in nature, which becomes the most challenging part. So let's dive into what these tables store and understand how the aggregate pipeline works. As mentioned in the previous slide, the daily job table contains the information of all the ephemeral objects which are scheduled for deletion. This table is partitioned into DS and execution date. DS is the date when particular objects are scheduled for deletion. Execution date is the date when the object is expected to be deleted. The aggregate table is the table which tells us which all objects are supposed to be deleted on a given execution date. This table is partitioned by execution date and index bit. Now, the execution date definition remains the same. Now, the index bit is the most interesting part. Let's assume the index bit we are talking about is Y. It holds all the objects which are due for deletion at a given execution date from some 2 raised to the power y days worth of data from daily job table. Let's understand this better with an example. For this example, we are considering the execution date to be 1st January of the next year, that is 2022. Let's say this pipeline was running from last 24 days and we have read the daily job table from the last 24 days for this execution time. On the 24th day, this is how the aggregation pipeline looks with the partitions for the given execution date. We'll have 4 partitions as you can see on the slides. Now, on the 25th day, when the daily job table gets all its objects to be deleted on our execution date, let's see what happens. We will find the smallest index that is not there and create it by accumulating all the smaller indices. In this example, as you can see, index 3 is not present. Now we create this partition for index 3 by joining the aggregate table partition for the lower indices and the incoming daily job table for the given execution date. As we have merged all the lower indices partitions to index bit 3, we drop these partitions. Now, hence, on the 25th day, after the aggregation pipeline is run, this is how the aggregation pipeline will look. Now we'll have only two partitions. Here, I want to highlight a few observations. As you can see, every row resides in exactly one index bit partition at a given time. Data is only moved to bigger partitions. As previously mentioned, this table is immutable in nature. Hence, we wanted to minimize the number of times a specific row is copied over to another partition. In this algo, each row only gets copied over after 1 day, 2 day, 4 day, 8 day, and so on. Hence, making this algorithm logarithmic in nature. Now, once we have the aggregate table ready, we now know what all objects need to be deleted on a given execution date. Before deleting the objects, we run the decision engine associated with the object. We do so because, as we previously mentioned about decision engines, they can be dynamic in nature and can depend on product logic. Now, if the decision engine returns delete immediately action, we pass this object to deletion framework, which handles the deletion of the object. We have the status pipeline, which contains the status of all the ephemeral objects. Now, sometimes when we are performing deletions, we might encounter some errors. Hence, we have the retry pipeline, which basically runs or retries all the failed and error entries every day. Now, suppose the number of retries performed on a specific object is above a threshold, we raise alerts and create tasks for developers to manually debug the issue. Now we know what objects need to be deleted. Now let's understand how deletion works at Meta. Before going into the infra, let's talk about some of the challenges of deletion. The first one is completion, which means that when the deletion starts, it finishes and doesn't error out in between. The next is coverage, which means that we delete all the data that is supposed to be deleted without leaving any data behind. The last one is correctness. We should be able to recover any errant deletions or any wrong data that is being deleted. Now let's talk about deletion framework. Before deletion framework was developed, each product team had to write their own logic to delete data, which could be error prone. For deleting the data, they would directly interact with the storage layer, which could lead to retaining data that should have been deleted or accidentally deleting the wrong data. Hence, we developed a central framework to handle the deletions. Developers can now rely on this framework to delete their data and meet all the three challenges which were discussed in the previous slides. Now let's understand the data model we have at Meta. We use the graph data model whose main entities are objects and edges. Objects are the nodes in the graph. For example, in this slide, it's the post. Now, the next entity is edges, which represents the relationship between objects. As you can see in this slide, we have an edge between the post and the photo attached to the post. We have the deletion field defined with the edges, which can be deep or shallow. When we have a shallow edge between the post and the user, when the post is deleted, the user is not deleted. Now, when we have a deep edge from the user to the post, the user is deleted and the post is also deleted. Now, let's understand how the deletion flow works. Suppose we have a famous celebrity that has deleted a post. We need to delete all the million likes and thousands of comments associated with that post. Now, this is it's not possible to delete all this data in one web request, as this data is spread across many storages. Hence, we divided the deletion flow into two parts. The first one is the synchronous part, which deletes the root node and instantly hides the subgraph associated with that object. The asynchronous part, which is the second one, it starts the asynchronous job which deletes the entire subgraph. For the graph traversal, we use the depth first search algorithm. Let's understand this better with an example. Now, when a user deletes a post, the post is deleted in the synchronous part. The comment and the replies associated with that post are hidden. Now, the asynchronous job is initiated, which deletes the rest of the graph. The relationship between the post and the comment is deep in nature. Hence, when the post is deleted, the comment is also deleted. Now, let's go through the key takeaways from this presentation. The key takeaways from this presentation are that we understood how we handle the deletion of ephemeral objects at Meta. We went through the scheduled deletion infrastructure, which uses the decision engine and aggregation pipeline to determine when to delete the ephemeral objects. Next, we spoke about deletion framework, which handles the deletion of the object. Now, let's talk about future work. As previously mentioned, the tables which we were dealing with for logging were immutable in nature, and we tried to use them in the most optimized way. But moving forward, we want to move to a storage which is mutable in nature and still handles trillions of objects with being cost effective. Next, we want to potentially move to a model where schedules that need to be deleted in the next 90 days are handled by one pipeline and rest by another pipeline. This will make sure that the current pipeline is less complicated and we'll save a lot on compute. Thank you.